a potential energy curve just like this one, except I have a ground, O2, this is our oxygen, diatomic oxygen atom. I can excite my oxygen atom to the excited neutral state, O2 star, let's say O2 star, which have a potential energy curve like this, right? But this O2 star potential energy curve happened to be above the ionic state, one of the ionic state of O2 plus, which have a potential energy curve like this. So what happened? What could happen is like this. If I excite my oxygen molecule with some photon to this excited state here somehow, right? And this excited state it doesn't like to be up there. It's excited state. So it's trying to go to a lower state. So it could go, of course, it could first return back to the neutral ground state. That's one pathway. The other pathway is that it can go to any other lower state. So, for example, you see all this line in the ionic state that you have, right? And so this is correspond, of course, not O2 neutral, but O2 plus an O2 ion. So if I excite this guy to an excited state, this excited neutral oxygen molecule will automatically ionize, so-called autoionization. This is the idea of autoionization. It automatically ionizes to an ionic state. In other words, it just goes through a transition from the upper state to a lower state, because that's just law of nature. It likes to de-excite itself, go back to the ground state. And this looks like a viable lower state, same as this one, right? The neutral ground state, but it can go to a ionic state if it's lie lower than this path. And then you will see ionization, P, just like this one, and that corresponds to autoionization. It's a two-step process. It's essentially a two-step process that generates these. So if you are in atomic physics or chemical physics, you will be interested quite a lot in this. For solid-state chemists, this is a secondary effect. So we try to avoid this because this tends to add another layer of complication to our understanding of what's going on. Okay, but in free molecule, you will have this type of autoionization to occur. I mentioned this so that people is aware when they are talking about these things. Okay, so I've been talking about this helium-1 photon. It cannot reach these deeper core state, but if you use a high energy photon, you could reach all the state, all the electron state down here. So here I'm trying to give you a description of these so-called, so what you just heard is helium-1 for electron spectroscopy, so-called ultraviolet for electron spectroscopy. So we start with, this is from the thesis of one of my friends when he was writing the thesis. You can make a picture like this. So this is my molecule, neutral molecule, 1s, 2s, 2p6, right? This is, what is this? This is you can think of this as a neon atom, right? Neon has this molecular atomic configuration. So you can think of it as a molecule or atom, doesn't matter. It's just a way to illustrate. So you use ultraviolet for electron spectroscopy, helium-1, which has 21.2 electron volt. What you could do, of course, you're ionizing ultraviolet radiation. You're ionizing the top level orbital. So you're ionizing the P's, the 2p and the 2s type orbital that you got from helium, from neon, if you'd like to think of this as neon atom. But if you use a deeper, more energetic photon, such as aluminum K alpha photon, and how do you generate aluminum K alpha? All you need to do, really, is to just excite it by, so you have aluminum foil. You take a little bit of aluminum foil, you parachute an electron beam with high energy. Let's say you create a high energy electron beam, 10 kilo electron volt, 10,000 electron volt, hitting your aluminum foil. And the aluminum foil, the aluminum atom inside your aluminum foil will get excited by this electron beam that you excite. And it goes to an excited state. And the excited state doesn't like to be in the excited state. It comes back down to the ground state, and it emits a photon. Okay, so this aluminum K alpha, meaning that you are exciting the aluminum 1s electron up to some upper state, and then this upper state comes back down to ground state and emit a photon. And this photon is always, because it's the difference in two energy level, this photon is 1486.6 electron volt, if you like. So it's quite precise radiation that you see. It's a single line. So aluminum K alpha line is about 1500 electron volt. Now, with 1500 electron volt, you could excite every electron in here because it has enough energy, not just the valence electron, but also the core electron, what they call core electron. So you can start exciting the core electron like that. You can excite the 1s electron. So here is indicating you can get rid of the core, or you can get rid of the valence electron. So both of these can occur. Ejection of the core electron, ejection of the valence shell electrons. Now, once you get to this, so now what happens if you take out a core electron? Well, what happened? Well, if you remove, in this situation, what will happen? What will happen is that this is not you have one missing electron in this deep electron hole, this electron orbital. Then this guy would like to fill this empty orbital. Okay, so the electron in the upper orbital would like to come down and fill this thing too, because that would be a more stable state. So you can do a fluorescent process whereby the upper electron will come down to fill this empty orbital, and it emit a photon. Okay, so the energy difference would be just correspond to the photon that you emit. In fact, this is how you create aluminum K alpha radiation anyway. Instead of exciting by photon, you are exciting the molecule. You are bashing the molecule with the electron, and then some of the core electron get ejected, and then the upper electron come down to fill this hole and emit a photon, and that happened to be 1500 electron volt in the case of aluminum, right? So that's a fluorescent, what we call X-ray fluorescent process. The upper electron come down and fill this hole. But there's another way of de-exciting the system. The other way is that you have one of the electrons come down, right, to fill the hole. And then, okay, so it uses up some of this energy, excess energy. The rest of the excess energy would then, can then be used to eject another electron out, okay? So this is a two-step process. This come down, and then the other electron come out. And this secondary electron that come out is called the OJ electron, and this is called the OJ process. Okay, so this is known as the resonance process, right? Because the resonance, because it involves two discrete levels. This is a non-resonant process because it doesn't involve light, right? Anything involving light is a resonant process because it involves complete absorption of a photon. You cannot absorb half a photon, right? You either absorb the entire photon or not absorb it, right? So if your photon energy is enough, you absorb the entire photon. Okay. So you have two processes: fluorescent process and resonant, non-resonant process, which is the OJ process, which this thing comes down and a higher lying electron will carry the rest of the excess energy out as kinetic energy, and you got this